First, I'd like to invite Director Fudeyasu-san to introduce Professor Yuchi-wan. Okay, thank you.
Okay, good morning, everyone. So it's the second day of the IWTRC, and we are starting the first session with a highly anticipated keynote lecture by Professor Yuchi Wang. So 14 years ago, I worked as a postdoctoral researcher at the University of Hawaii under Professor Wang. So today, I'm deeply honored to invite him to the workshop where we will have the pleasure of hearing Professor Wang's special keynote lecture. So, but before we proceed, so allow me to provide a brief introduction to Professor Wang. So, Professor Yuchi Wang obtained his bachelor's degree in metallurgy from Zhongshan University in China. So, my pronunciation was maybe incorrect. But the master's degree from the Chinese Academy of Metallurgical Science in Beijing, China. So he completed his PhD in applied mathematics at the Center for Dynamical Metallurgy and Oceanography in Monash University, Australia, under the supervision of Dr. Greg Holland in 1996. And he worked as an assistant researcher in Shanghai Typhoon Institute, so China, from 1988 to 1991, and as a senior professor, professional officer in Australia, Blue Metallurgical Research Center from 1996 until he joined the International Pacific Research Center as an associate researcher in earlier 2000 and became a faculty member in the Department of Atmospheric Science at the University of Hawaii at Manoa in 2004. So over the last 2 years, Professor Wang has made a significant contribution to the field of tropical cyclones, tropical metallurgy, and regional climate modeling. He is a widely acknowledged expert in the technological metallurgy, tropical metallurgy, especially in the tropical cyclones, with his research findings featured in the over 240 scientific papers in refereed journals and received over 50,000 citations. So under his mentorship, I conducted research and learned a great deal from him. So I credit much of my current work as a typhoon researcher and director of TRC to Professor Wang's teaching. Therefore, I'm truly delighted to have the opportunity to introduce Professor Yuchi Wang to all of you here. So I hope you all enjoy Yuchi Wang's fantastic lecture. So the title is up. Please go ahead. So title is Unified Time-Dependent Tendency of Tropical Cyclone Intensification and its Application, Current Status, and Future Direction. So please, thank you so much.
It is my great honor to participate in this first workshop organized by the Japanese community and in particular in the Typhoon Research Center here. So as Fudeyasu mentioned, I also have a chat with him yesterday. I gave him homework when he was a postdoc in University of Hawaii. I say the Korean, they established a Typhoon Research Center in China. I have a Typhoon Research Center by that time. And I say, that's your homework to establish a Typhoon Research Center in Japan. So after 10 years efforts, he succeeded. So I'm so proud of Fudeyasu-san. And also would like to thank the organizer of the workshop, and they invited me and arranged everything very delightfully. And also the Professor Sato-san arranged my trip to the University of Tokyo and also the visit to Kyoto University next week. So I'm so grateful to Dr. Sato-san's help and the support. Okay, so my talk today, and because I think the three lecture talks is quite interesting, carries no any formulas, equations, and Chenjie have many numerical experiments, but then turn to me, I have no experiments, almost, but with some equations. So so-called the unified theory is not really unified, but I just use the word to indicate that the one framework doesn't matter from which angle you can get the same solution. Okay, so so far I will talk about the time-dependent theory from the Carey's work. That's more than 10 years ago. So I really appreciate Carey's work. It stimulated my thoughts, and I really spent time to understand his theory, and then eventually I get I think it's a simpler way to get the equation, and also we can get the more understanding on this framework. So, and also I have some collaborations with my friends and colleagues, and also my former students, and we developed a theory, but also we focused mostly on the applications in the current stage. And also I will discuss some future directions in my mind, and I hope I can do more work in the coming years. So I should acknowledge my colleagues and former students and postdoc. For example, the Jing Xu is also attended this meeting today. And the Yuan Long Li is also a PhD student, former PhD student. He is now a postdoc in Nanjing University. He also a PhD student several years ago. And also Zhen Mingtang is I think is my best friend in China. He's president of Nanjing University currently. And also we have a lot of discussion in the early stage of the development of the theory. Okay. And also Riven Zhang, she also sitting in the room, and he advised the student to apply the theory to perform some forecast development. So that's my team you can consider related to this work. Okay, so this is the outline of my presentation. So first, I will give very briefly the classical views on tropical cyclone intensification. That's the current understanding. And also then I move on to the theory and the early efforts toward the time-dependent theory that started from Carey's work. And of course, I couldn't give all details, but I just bring the key points and the main results and the conclusions. And then I will discuss and also I will mention about some weakness or some assumptions we should improve. That's the way we can move forward. So that's following the early efforts, and I will introduce my own work, okay, from my group. And there are two ways to get into the equations. So the series, that means so we have two different ways, and eventually reasoning. And when I prepared for the workshop here, and I consider, that we can unify it. So eventually I give the unified, how that means unified. Okay? And I will spend most of the time to introduce the current applications. So the theory can be used to quantify the environmental effects on tropical cyclone intensity change. That's based on the observations, not based on the equations. Okay, but start from the equations, but we use the best track data, and then you can see, and also reanalysis data, you can see how the different environmental factors contribute to the tropical cyclone intensity change in observations. And following the application, the second main application is the prediction of tropical cyclone intensity. Okay, so this is just in the initial stage of the development in this direction. but I will share with you about some preliminary results. I think it's very encouraging. So I only bring the results for Atlantic, but we have the scheme for the West North Pacific also to show the promising results as well. So I will share with you some initial results. And finally, very briefly, and the future directions in my mind, in particular, what's based on this theory, what we can do in the future, in the near future, not too long future, but the near future, like I said. Okay, so the first, I will give you briefly what's the classical view of tropical cyclone intensification. I think from the textbook anywhere, you can know maybe you can consider the tropical cyclone intensification is the warm core formation and a low-level convergence and the upward motion and the condensation or heating in the I-wall region. And then there are, from the balance dynamics point of view, you have the heating in the I-wall and then drive the secondary circulation. The inflow in the lower troposphere can bring the angular momentum in and spin up the tangential wind. That's the intensification stage processes. And also there are upward motion and then you have descending motion in the I region. So we still have debate on what's the mean, the warm core. The warm core is a passive or active region. Okay. So there are some say the warm core is caused by the substance. That's called the forced substance. But the other way is the summer wind balance needs the warm core structure there because your tangential wind is decreased with height and you must have a warm core structure there. But that's from a different angle, different point of view, but the same thing, okay, same story here. This is not what I want to say about the intensification, but we just theoretically, for understanding, for class teaching, we need to simplify and conceptualize of the intensification processes. So far, I can summarize. Of course, there are some other series, but I think the textbook is dominated by the three main series. Let's see, one is the CISC in the early days. I believe carried against this mechanism very much at the beginning. But I will introduce a little bit what does it mean, the CISC. The second is the conditional instability of the second kind. That's just a distinguished, is different from the first kind of the instability because it's involves different scales. The first instability is just the vertical column tossal instability. And then also in the 1982, that's the balanced dynamics. This one is mainly of course is the positive feedback, but by that time there are no clear discussions. What is the feedback? What's just the diagnostic approach by that time. And then I think this is a very dominated theory currently. Junjiu will talk a lot about the wish. So this is the wish carries theory. That's I think is so far is in the mainstream in the textbook is dominated by the wish theory, particle cyclone intensification. Okay. So the point is here is all these theories are qualitative descriptions, no quantification. No quantitative description of the intensification rate. If we want to understand the intensification, of course, conceptually is important, but how to quantify? Give the intensification rate. That's the theory. Otherwise, it's still considered the hypothesis. So why wish is a theory? Because based on the wish mechanism, Perry developed the MPI theory. That's a theory. Can quantify how strong the storm can reach. This is the upper limit. That's the MPI theory. This is theory because you quantify. But for the intensification rate, based on these at the current state, there are no one theory can quantify the intensification rate, except for what I will discuss, the early effort from the Paris 2012. So that's the early stage. I can say this is most of each of the mechanism or theories just emphasize a certain positive feedback processes. Okay, I will introduce the three very briefly. Okay, first I use this cartoon figure from the Horton's book, but I add a lot of words and the feedbacks here. So the wish is a mechanism induced by the boundary layer merge convergence. But the moisture conversion is also due to the low pressure system and the frictional inflow, and bring the moisture and then Ekman pumping cause the upward motion, descending upward motion, and then cause the condensation or heating, support the convection in the inner core region. That's a CISC. Because you have a convection, and then they warm the column, and then cause the pressure down. And the pressure down, that's it brings the more inflow. This is the positive feedback. For the wish, I also discussed yesterday about the wish. The wish carrier also probably agree there's a positive feedback between the wind and the surface flux. So wind increase causes the surface flux increase. Surface flux, of course, that's the enthalpy flux, or we consider that's the energy source for tropical cyclone intensification. So here, why the wish is different from the CISC. CISC is the global convergence. Okay, that's large scale convergence in the boundary layer. But wish mainly focused on the interaction, on the local interactions, on the IOR. Why is it local interaction? Because the wind is always increase for tropical cyclone intensification or rapid intensification. The wind only increases in the inner core region. Outside the wind doesn't affect by the intensification processes. But bring some wind up, but not significant. Okay, so mainly the wind increased in the inner core, near the radius maximum wind. So this is a positive local, mainly the local feedback. That's also I discussed yesterday. Let's say whether we can cause the wish and far away from the core region. Okay? That's my comments yesterday. So I consider the carrier theory originally is a local feedback, mainly local feedback on the IOR region. Okay? So CISC is different because the converged moisture can come from a large area. Okay? So this is different. One is focused in the local region. So this is very important. I think important or also efficient for us to think about theoretically what's going on. Okay, because it's hard to control the large scale moisture content and the surface flux outside far away, whether it's a positive or negative to the tropical cyclone intensification. That's the thing discussed yesterday. Okay. So based on the CISC, you need the more high moisture in the boundary layer, but the boundary, if they cut off the surface flux in somewhere or reduce the flux, and then suppose the air becomes drier, the inflow brings the drier air. That's unfavorable for convection in the IOR region. It's just the opposite. Okay, but the wish is just to say the local doesn't matter what's happening outside, but indeed need the drier outside region, not the moist outer regions. So that's quite different in by the two feedback mechanisms. So for the balanced dynamics, balanced vortex dynamics, we can trace back to the 1950s. Okay, from the Eliasson work. So the story is mainly focused on if we have given the heating in the IOR region, and then you can get the balanced response of secondary circulation. So that means the inflow in the boundary layer, upward motion in the heating region, and then the outflow at the top. So inflow in the boundary layer can cause the speeding up of Keynesian wind. You can use the Keynesian wind budget equation. Here, the first term is the radial flux of the absolute velocity. So in the tropical cyclone, for a tropical cyclone or tropical depression, normally we have the high relative velocity. Of course, absolute velocity is also higher, elevated in the inner core region. And if you have the inflow, of course, this term becomes positive. This can cause the tensile wind increase. That's the low levels. Of course, there are upward motion. That's the vertical elevation. That means this is the vertical motion at near the radius maximum wind. Because if we talk about the intensity, I just intentionally use the max. That means near the radius maximum wind region. And the vertical elevation near the surface, of course, is very small. But away from the surface, you can get in the IOR region, you get the vertical elevation. Okay, so that means the spin up of the IOR region. That's mainly caused by vertical elevation instead of the horizontal elevation. But in the lower part of the boundary layer, it's mainly the horizontal inward flux of the absolute velocity dominant term. And then we have the frictional term, that's or vertical diffusion, and also there are horizontal diffusion. We will not discuss the horizontal diffusion here today. Okay, But the vertical diffusion is including the surface friction. If you use the slab boundary layer, of course you can use this term, approximations. Okay. So just to say the thickness of the boundary layer and that's the CD. CD is the drag coefficient at the surface. This is the surface wind, and you can roughly get this equation here. So based on this equation, if we ignore any asymmetric structure, and then we can consider the axisymmetric spin-up. So based on this equation, we can consider the two components. One is the term can contribute to the spin-up of the storm, okay? And the other part is the spin-down. So for the spin-up part is the intensification potential caused by two terms. And then the spin-down, that's the frictional weakening, just this term is negative here. Because this is positive, definitely positive, okay? So this is the negative. So we can consider if we want to understand the intensification process of tropical cyclones, of course, we have to focus on two variables. One is the absolute velocity in the inner core. The second is the inflow, what drives the inflow. Okay, so based on the balanced dynamics, we can let's come to this cartoon here. We have the I-wall heating, and I-wall heating, of course, can bring inflow. Of course, inflow can support the heating as well. Okay, this is the positive feedback as well. And then we have the inflow and the stronger inflow, large heating. For example, we have the stronger inflow. Stronger inflow in the inner core region, the absolute velocity is high already there. And then this is cause large tendency. That's the intensification. If the large, that's the increase of the tangential wind. Tangential wind increase, of course, if the rate maximum wind change slowly, for example, and then we have the absolute velocity increase as well. But during the intensification of the storm, the inner core relative humidity, relative velocity, or absolute velocity also increase. So increase this term and also contribute to the increase of the tendency term. So because you increase this term, either increase this and increase this, you can get the larger or higher intensification rate here. So this is the positive feedback you can see. So the tendency, large tendency causes a large increase in tangential wind. Tangential wind increase can increase the absolute relative, the absolute velocity. So absolute velocity increase and also increase the tendency. So this is become the positive feedback. So this is I consider this is what the balanced dynamics try to tell. That's a positive feedback. However, you can see what's uncertain here. What determines the heating rate? In this theory, there are no closure. So just a diagnostic approach for understanding. And with this approach, you can specify the heating, either how strong the heating and how far away of the heating source from the rate maximum wind. You can determine the different intensification rate. But it doesn't tell you what it determines the location, rate of location, and the magnitude of the heating rate. Okay, so this is your diagnostic, not the closed theory. So this is the summary of what I consider is important for the thinking. So the first, based on the classical view, the qualitative description mainly just one kind of the positive feedback processes, okay, like a CISC and which I mentioned already, okay, and also balanced dynamics. No one is quantitative description of the intensification rate. So the new efforts, that's the efforts, I think, as I said, from a decade ago, that's from Kerry's work, and to quantify tropical cyclone intensification rate, to give the equation, the rate, we can determine the rate, how fast of the intensification of the tropical cyclone. So this is based on some, of course, principles, either physically or dynamically or energetically, I will introduce today, energetically or dynamically, okay? So based on the time-dependent theory. So this is based on equations. So this is I think that's a new area in the last decade or so up to now, and we still make our efforts to enhance our understanding, in particular the quantitative understanding of tropical cyclone intensification. So I think the development of such a theory is very important. I just listed two. Probably you can add more, but I think this two is the key. For example, the first is the significance of such a theory can be considered as a theoretical basis for understanding climate change impact on tropical cyclone intensifications. Because currently there are some studies to look at how the global warming may affect the tropical cyclone intensity. That's when we have the mature theory, like the MPI theory, and also there are some observational studies currently focusing on how the tropical cyclone intensification rate or rapid intensification can be changed due to global warming. We need some theoretical basis to understand such a change. And secondly, the theory, if the theory is good, and of course should have a potential to be used as a tool, or based on the theory can develop some schemes to predict the tropical cyclone intensity. That's the application side. Okay, so based on this, I think this is important, and we should do the efforts. So let me introduce some early efforts here. Okay, so there are two efforts so far, and I already mentioned several times about the Kerry's 2012 work. So Kerry based, I consider it's a dynamically based theory, time-dependent theory, because it's started from the not a slab boundary layer, but the integrated, eventually still a slab boundary layer. I think Kerry will agree with me, right? Slab. So we started the slab boundary layer entropy and the momentum budget equations. Of course, different coordinates we used and I used. We have a different coordinate, but the same equations almost. And also, he assumed the very key assumption is the moist neutral IOR convection or ascending motion above the boundary layer. So the slab boundary layer in the boundary layer, and then also the IOR ascends. That's the moist neutrality conditions. Okay. This is the first, I think more than 10 years ago. And another theory, I think that's developed by the Japanese colleagues and the Adawa and the Shimokawa. Okay, so this work didn't receive too much attention. I think that's mainly because the paper published in TELUS. Okay, that's the European journal, traditional journal. Okay. But it attracted my eye because I have the same thought before their work. So you see, the idea also I put in my review paper in the same year as in 2012. So I have some ideas on this, and then they succeed to do it. Okay. So what's the energetical based? That's the time dependent theory. That's mainly consider the tropical cyclone as the unsteady Carnot heat engine. So Carnot engine you can consider different ways. That's the steady state or the unsteady state. Maybe the word is not good for this, but I think it's good for our discussion today. Okay, we can discuss what's the best word we can use. And then he assumed the Borg energy conversion rate, because based on the Carnot heat engine, if the unsteady, of course you can have the energy gain or energy loss for the whole system. And then if you assume some relationship between the energy gain and how much energy can convert to the inner core winds, okay, kinetic energy. So this can give it some quantitative measure of the intensification rate. So here, I started this because this is simpler than the dynamically based theory. So I started from the Carnot heat engine one. Okay, so for the so-called the unsteady Carnot heat engine, that's just the extension, just some extension. Okay, because before this figure shown, I believe that's everyone knows here. That's the Kerry's MPI theory. MPI theory, that's the energy. If we have the horizontal axis is the intensity or the wind speed on the IOR, and the vertical coordinate is the power or the energy input or energy dissipation rate. That's what we call the power. And you can see the energy, the power dissipation often is a function of the cubic of wind speed. But the energy input or the power generation is the linear function of the wind speed. So then you can have two curves. One is linear, one is nonlinear. So what's going on here? So this friction at the beginning seemingly smaller. The dissipation is smaller than the energy power generation. So this is the positive area. Of course, there are negative here. That's a negative here always. Suppose we have a negative here, okay? And then at this point, the power dissipation just equals the power generation. Where this point? This point is the MPI. Because if the storm further to develop, further intensify, and then frictional dissipation will be larger than the power generation. So that means there are no room to further intensify for the storm. So in my review paper in 2012, I proposed this. I used this cartoon figure, and then I show the area here. So what's the area here? What's going on here? That means that before the storm reaches the maximum intensity, and most of the intensification, the energy gain here, the positive area here, that's most of the energy the storm can use to intensify. Okay. So based on this, of course, you can write a simple equation here. This is the kinetic energy, because the energy intensification, of course, the kinetic energy increase of the system. And then if this is the positive, of course, you get the intensification. That's the intensification processes. So the key to complete this theory is how to formulate the kinetic energy conversion of the system. Because we have the equation for the power generation and the power dissipation. Okay. So I think the Japanese colleagues, they did the effort first. So this is just a repeat. I rewrite the two terms, and then we just put the two terms together. That's the energy gain rate. I consider it the energy gain rate. That means the energy input and energy dissipation, there are positive differences here. And then, of course, there are for the power generation, we have already have an epsilon here. So I should remind you, we have a thermodynamic efficiency. That's Carey introduced in his MPI theory. That's almost the same. We didn't consider the thermodynamic efficiency may change with the intensification processes. We just consider this nearly constant value here. Okay, so in Ozawa-san's work, they introduced one mu here. That means not all potential energy can be converted to the kinetic energy. So just a part of the potential energy can be converted to the kinetic energy. That makes sense because if you have the heating, you increase the potential energy, only part of the potential energy can convert to the kinetic energy because some gravity waves, okay? In particular, when the storm is quite weak, the weaker stage, but the mature stage may be efficiency higher. So this is the mu. This is not determined. Okay, that's just the empirical coefficient here. So they assumed this coefficient is around 70%. Okay, 0.7. This is the heat energy can be converted into the inner core kinetic energy. Okay, so then the energy gain just increase the energy in the inner core region. So this year they assumed this is just a function of the kinetic energy just determined by the maximum wind of the storm. This, of course, this brings some errors. We suppose the whole column of the inner core, the intensity, the increase of the intensity. And also the wind speed is not uniform in the core region, but they just assume this is the uniform. So based on this, that's the equation they can have. You can see the mu here now, still here. And this is the CD, that's the HS is the depth of the inner core, the column of they usually they say 8 kilometers. That's the equivalent depth of the troposphere. Okay. And this is the MPI. MPI is determined by or mainly this term. This is Carey's theory. Okay. So this you can find anywhere. Okay. So, this is the first theory. Not the first, okay, the second theory, but I introduced it first, okay. So and then we move on to the Carey's theory. Carey started from the two equations. This is the entropy budget equation in the boundary layer and the angular momentum budget equation here, okay. So the vertical integrand of two equations, that means the equivalent to the slab boundary layer, is what I mean. But the carry uses the angular momentum coordinate. Use this coordinate, you can simplify the angular momentum equations. Okay, that's you don't need to consider any radial elevation here, this equation. Okay, so use this to substitute this equation, this term into here, and then you can get the one equation. Right? But the key for this is how to determine this term, and how to relate to the entropy to the wind. We have a lot of math. Okay, so my math is not as good as Carrie's. I haven't done the math by myself, but I show you the results later. Okay, so I will not skip all details of the math. Okay, so here I just summarize some key assumptions Carrie used. Maybe my summary is not correct, and Carrie can correct me here. So the TC is assumed to be axisymmetric and in some wind balance above the boundary layer. I think that's not question. The second is the radius of maximum wind is nearly a material surface, and thus the angular momentum, relative angular momentum is nearly constant. That's in the derivation. I can see there are one line showing this as approximation used. And the last one, I think, is the more critical one, is the absolute angular momentum surface and the saturation entropy surface are nearly congruent in the Iowa region. Or similarly, say the Iowa sand is a moist neutral conditions. This means the entropy, the absolute angular momentum surface and the entropy surface is parallel, congruent. Okay. So based on these assumptions, and that's eventually the results, the integration rate equation, very good. And I even discussed with him this morning, and about the CD and the CK. Okay. So you compare the energetically based time-dependent theory and the dynamically based theory. You can see the differences here. So the formula is very, very similar. The first term just to describe the integration processes. The second term is the weakening, the dissipation processes. So from this, of course, there are MPI is different. Okay, maximum intensity here is a little bit different because this uses assumption for the closure of the MPI theory. One is in this new work, 2012, Harry used the closure from the outflow layer, assumed the turbulence that I'm mixing give the vertical Richard number, okay? And then he got the different MPI mathematically. But differences in magnitude is not very significant, okay? But just the physical basis is different. Okay, we compare the two theories. You can see the very similar, but just some different. The two differences here. I should remind that here is a CK, here is CT, and that's the denominator. Here is 2H. H is the boundary depth of the boundary layer, but here is the depth of the atmosphere, troposphere, around 8 kilometers. But carry uses 4 kilometers for the boundary layer. We're mixed boundary layer in some papers, but in some papers use 2 kilometers for H. So I don't know which is the best or which is the more appreciated. But currently I use the 2 kilometers. I can tell you, okay, 2 kilometers is based on the full fixed model simulation and also based on observations. Okay, so because of timing, I explained very well for the early efforts. So we used this to verify the theory using numerical model simulations. Okay, so the dashed curve is the theoretical intensity evolution. You can get the analytical solution for this. And what he found, he said when the storm at the weak stage, the theory couldn't capture the integration rate. And he considered this is the moistening of in the model. Okay, the model takes time to spin it. And also for the different scientific experiments, got the similar results. Okay, change CK and change CT. Okay. And what attracted my attention is if we check the curves carefully, you will find the results can comparable after 30 meters per second. Before the 30 meters per second, the difference is small. above 30 meters per second. But in the weak stage, not a spin-up stage, not a spin-up. That means the moistening of the boundary layer may explain to some degree, some content of the discrepancies, but not the all. And Harry and Fuchen Zhang also they did an effort to add one more equation, moistening equation and the time-dependent equation again, and then try to reduce the error in the early stage. But in my view, it seems there are some missing something else, not just the moisture. Okay, so I consider some, I can say the weakness or incompleteness, incompleteness. Okay, not say that it's wrong, but they just say there are some room to be improved in some way. Okay, so first, based on this equation I already shown you, the dissipation or weakening potential of the tropical cyclone determined by the CD. So from this equation, it's clear. But in the theory, current similar, for example, let's say with CD. CK contribute to the intensification. That's good, but not contribute to the dissipation, supposedly. So this is one of the inconsistency. The second is if we compare if we look at the assumption of the neutrality condition in the IWTRC region, but this seems the only good approximation, good assumption when the storm becomes quite strong or mature stage. So this is a work from the Penku paper. So this is the initial condition. You can see the angular momentum surface like this, or baroclinic vortex, and this is the isentropic surface. Okay, isentropic surface. And here, this is the mature stage. You can see the momentum surface almost vertical here. And the entropy surface is also almost parallel. So this is the neutral condition, but this is not. So this means the assumption is the free atmosphere, how far to the parallel, to the concurrent between the angular momentum surface and the entropy surface should depend on the intensity of the storm, not all the time. Is the neutral conditions. Okay. So we try to improve this part, okay, in our later stage. So this is the motivation, okay. So then we try to fix the problem. Okay. The first, we can see this is the black curve is just based on the two equations. Okay. It doesn't matter is the energetically based or dynamically based. So we can get the intensification rate is the maximum when the storm is quite weak. So this is suppose the storm at the weak stage should intensify rapidly, but that's not true in the world in reality. Okay. However, if we just this is the observations. The observations show the maximum intensification rate often occurred in the intermediate intensity, not the weak intensity. So only the 30 to 40 meters per second, and the storm can get the maximum intensification rate. That's the observation shown us. So what we can do? What's the problem in the early work? The first, for the energetically based, I said we already see, right? Mu is 70% used in they assumed the constant, 70%. However, if you have a 70%, then you have trouble. We have trouble because in the steady state, the V max only 70% square root of the MPI. That doesn't make sense. Because if the theory can explain the intensification processes and also can explain the mature stage, but here at the steady state, this is smaller than the MPI. So the mu is a constant. It doesn't make sense. Should be improved. Okay, so that's my work. That's very simple. I'm not very smart. Okay, I just change one parameter here. I don't change too much. Okay. So just an exercise. Okay, I introduce, based on the balanced dynamics say the intensification and the positive feedback in the inner core region, inertial stability, or the absolute velocity. absolute velocity and is proportional to the inertial stability. Okay, so I just introduce a parameter. So normalized inertial stability. So this determines the mu. It seems to make sense because when the storm is quite weak, and there's most part of the energy, potential energy, become the gravity waves, propagate away from the storm inner core region, couldn't concentrate in the core region. But as the storm intensified, become very strong, and the energy can capture in the inner core region because the Rossby radius of deformation becomes very small. Okay. So here we use this, and we just give the number n here. We don't know what's n, how it is, but it's greater than 0, of course. And then we just use 1 and 2, do exercise. I just do my homework, and then we calculate it. So this is 0.1, 0.5. This is 1.0. We just introduce one parameter here. That's the intensity dependent and also size dependent. Okay. So we use this, and we can get the curve like this, very similar to observations. This is really motivated me to consider how we can make some corrections. Okay, so that's why I said this modified energetically based time-dependent theory. And based on this, we do the numerical modeling to verify. Okay, so the model we use here, we just change. The H is very sensitive. Okay, we use the 2,000. That's mean 2 kilometers. We get quite good results instead of the 8 kilometers in the original paper. Okay, we found the 2 kilometers gives the best results. Okay, so we did a lot of experiments. Okay, so I show you the 2 columns here. One is just to show you one results based on the Western Pacific. We have a different ST and different sounding from the Pacific. Okay, that's the climatological summer mean. Okay? Summer mean sounding. So we did for example, the 28 degrees Celsius and the 31 degrees Celsius, the different ST. So this column showing you the time dependence. The horizontal axis is time, the vertical axis is the intensification rate. And the right-hand side, we just change the coordinate. This is the intensity of the storm, Vmax. And the vertical coordinate is the same, that's the intensification rate. What you can see here, one is the simulation, yellow ones, and then the green one, that's the intensification rate from the equation. From the equation, I just modified. So you can see, based on for the time dependence and the intensity dependence, so this gives the results very much like the numerical results. Okay, and also can be comparable with observations. So I think this is even just one parameter change. Okay, but it's changed the whole characteristics. We call it the intensity dependence of the tropical cyclone intensification. Now we can capture because we introduced the dynamical efficiency here. So we call this E. That's called the dynamical efficiency. That means how much potential energy can be used to convert the kinetic energy of the inner core of tropical cyclones. But it's intensity dependent, not the constant. Okay, so then we move on to the second, another part. That's the dynamically based. I used a new dynamically based time-dependent theory, and Kerry may not agree, but one of the reviewers also say that's probably not a new theory, but it's just an improvement. I agree, that's an improvement, but I can say there are some new ingredients. I still use a new, and then other editors also accepted that's a new theory, but it's just an extension. I consider this an extension of the Kerry's work. Okay. We fixed up, of course, there are some key assumptions, as I mentioned. Okay, so we started with the following slab boundary layer equations, but not in the momentum coordinate, but we used just the Cartesian coordinate. And this is the tangential wind budget equation, and this is that's the entropy budget equation. Slab boundary layer, there are no vertical elevation. Of course, there are some exchange. There are some small terms. There are exchange between the boundary layer and the free atmosphere, but we just ignore it. We just consider this under the IO region. So this exchange is because the upper motion dominated. There are no much exchange. But we introduced one parameter beta here. That's the efficiency of the parameter describing the effects of the subsaturated or downdraft. Again, under the IO region, that's nearly 1. Okay, that's not a big deal. But outside of the IO, this term should be important. Okay, and we also assume that the boundary layer is in thermodynamic equilibrium. This is a very tough assumption indeed. However, this is an assumption used in some previous studies, and also observation shown some similar support. This is a assumption. And Kerry also used this for assumption for the cumulus permeabilization. Similar assumption, but different explanations. Okay. So this, if we assume the quasi-equilibrium, that means this term can be ignored. I will show you from the full physics model results, that's a good approximation indeed. With this approximation, we simplified the whole mathematics. That becomes very simple. We substitute this term into this, and we get this equation directly. So simple. But we just need to determine this term. So the boundary layer, so this is the surface flux, this is the frictional dissipation. Also can calculate it, indeed. Okay. So the question is how to determine this term. Before I move on to the unknown, we try to determine, and then I just support the hypothesis. Okay, the assumption. We assume that the neutrality, the quasi equilibrium. Okay, so this is well supported. Okay, so this is the entropy. The theta E is equivalent to the entropy equation. Okay, so we have the time tendency and the advection term and the surface flux and the horizontal diffusion. So the model output, we didn't have the output for this term. You can see the 3 terms. Time derivatives, that's the tendency, quite small, following the red maximum wind, of course. Okay. That's not the outside of the IO. So near the IO for all the ST, and for the Atlantic, for the Western Pacific, we did the simulations with a different ST, different sounding. We got very consistent results. You can see the advection is negative and flux is positive. They have almost the same magnitude, but a different sign. One is positive, one is negative. So that means the 2 terms must be balanced. That's the quasi-equilibrium assumption we use. That's supported by the numerical simulation results. So you can see when the storm started intensifying, of course, in this stage is a spin up, moistening of the boundary layer. But when the storm starts to intensify, you can see the 2 terms dominated and also nearly balanced. So this is the assumption is supported by our full physics model simulations. Okay, and then we move on to another term. That's the only term we need, okay, to close the theory. We also follow the Carey's theory, summer wind balance. But in Carey's work, I mentioned the M surface and theta E surface and most saturated entropy surface is the parallel. It's a neutral conditions parallel. Okay, so what we did, I introduced a new ad hoc parameter, A prime, so to measure the degree of the concurrence between the 2 surfaces. So just to modify this term, just to introduce 1 parameter here. So this parameter, of course, must be greater than 0 and less than 1. Because if this is becomes 1, the summer wind balance. That's the neutral conditions. But if 0, that means the angular momentum surface and entropy surface is not the parallel, but the perpendicular. That's like the initial stage of the tropical cyclone. So that makes sense. Okay, with this assumption, we can change the equations. Eventually, get this equation. Okay, so you can it's easier to get. Okay, so because this you can use the MPI to substitute this, and then we get this equation. Okay, so now the A becomes the beta times A prime. Okay, so this A we don't distinguish the differences between beta and A prime because the beta is nearly 1 near the red maximum wind I mentioned. Okay, so mainly is the A here. So how to determine the A? I don't have a theory. This is the only black hole in my theory, okay? What determines the A? Even theoretically we couldn't get it, but we can get it empirically. Empirically, how we can get it? Because we have the equation already. We have numerical results. In the numerical results, we have the intensification rate, we have the MPI, we have the intensity of the storm. We can inversely to find the A based on the model output, just the inverse problem. Okay, our results shown, this is the function of the relative intensity. This makes sense. When the storm is weak, nearly zero A. Okay, once the storm reaches the MPI, that's become the 1. But the N here, we need to determine based on the numerical model results and or observations. Okay, so eventually we get the N equals the 1.5. Okay, let's see. I show you how good it is here. That's just the fitting based on the best track data here, and it's based on idealized numerical simulations. So you can see the purple one curve and this is the green one curve. You can see matches the model results observation quite well. So that means we can use the N equals the 3 over 2, 1.5. This is best. Use this, we can get the equation become closed. Okay, so you can see how good we use a numerical model to see the model result compare with the model results. Theory is just the 2 terms there. Okay, in the numerical model is a full physics model. That's a CM1 model. Okay, of course it's axisymmetric because the theory is assumed the axisymmetric structure of the storm. Okay. So we have the different sea surface temperature, and I mentioned we have the Western Pacific sounding and Eastern North Atlantic sounding and ST. You can see the solid line is the model results, and the dashed curve is the theory, gives the intensity evolution. You can see how good of the theory compared with the full physics model simulation. Of course, there are some discrepancies. Okay, there are some discrepancies, but I think it is acceptable compared with the earlier results. Okay, earlier results give the pump is immediately instantaneous rapid intensification of the storm, but here gives the slow intensification and then rapid intensification and then reaches the maximum intensity. So this is the dashed line calculated based on this equation. Okay, so compare with the numerical model results, of course, is one aspect. And also we should compare with the observations. Of course, you might consider observation, and there are many environmental effects, and there are uncertainties in data. Yes, I agree with you about those points. However, we can look at the maximum intensification rate. That means the top 99%. That's a lot of storm in the Atlantic, Eastern Pacific, and the Western Pacific. That's a global, or mostly the global northern hemisphere or tropical cyclones. We plot the all intensification rate, okay, and then we just choose the top 99%. That means these storms affected by the detrimental effect of the environment, very minimum, okay, minimum effect by the detrimental effect from the environment. Okay, so you can see this is the top panel is the user best track data. We just calculate each location of the tropical cyclone, and then we get the intensification rate as theoretical estimate of the intensification rate. But the lower panel is just the top 99% from the historical data. So you can see the distribution is quite similar. For this case, we have the intensity. This is the relative intensity. So we just ignore this part. Okay, we use the relative intensity as a horizontal axis. So this is the MPI. The color showing you intensification rate. So what do you see here? This is about the relative intensity at around 0.6, get the maximum intensification rate. Theoretically, and also in the observational data. So that's very consistent. So that means it's a bigger improvement for the theory. So then I should spend just one slide showing this is the unified. What does it mean, unified? Unified, that means the equivalence. Because for the energetic vertically theory, you can see how we get it, that is the 2 terms, right? But dynamically, we use the budget equation and assume some assumption for the free drop sphere. But here, so the energetically based, we just improved, for a comparison, we re-evaluated the energy conversion term here. In the earlier work, you can see they used this, just the proportional to what? To the maximum intensity of the storm. But here, I just say this is the volume. This is not the case for this, but it's volume averaged wind in the column. The volume averaged, because the tangential wind is not uniform in the column, okay, up to the 8 meters per second or whatever, 8 kilometers. But we use this, and then you can get the equation like this. And we assumed the mu, this mu is different from the 70% mu there, okay, in the early work. But just to say, the mean wind in the column, the ratio with the intensity of the storm is 10 meters per second height wind, 10 meter height wind speed. So we introduce the new H scale. We scaling the H. Instead of the H here, we use this, and we get the same results here. Only difference is the E here is the dynamical efficiency. But the A, we explain the A in a different way. Because the A is introduced to measure the moist neutrality. That's a ventilation. If you have any ventilation from the dry air intrusion or vertical wind shear, we can reduce the ventilation. We can increase the ventilation. Increase the ventilation, that means reduce the A, and destroy the neutrality. So the A and E, they have different explanations, but they have shared the same mass formulations. Okay, so this is still the relative intensity and the power 1.5. Okay, I don't have time to discuss the written work, and if you are interested, you can see some refinements for the current theory. And this is the JS paper, the first issue of this year. Okay, and Professor Harry Maynard is one of the reviewers. He provided a lot of motivation to my improvement of this paper. Okay? So in particular, the isosomer effect, and I don't have time to introduce all details, but if you are interested, you can read this paper. Because with the background today, you will be easier to read these papers. Okay? So, but I should just very briefly, we include the dissipative heating. Dissipative heating, that's also encourages MPI theory. Also, there are several works. There are two extra terms. I will not discuss here details, but I just show you with the dissipative heating, and then we improve the results compared with observations. So these are observations. So here, we haven't included any dissipative heating, and the red dot is the observational intensification rate as a function of the relative intensity. But the darker one, the black one dots, that's a theoretical theoretical intensification rate. So you can see the envelope, supposedly the theory supposedly is just at the up top envelope of can cover the intensification rate of here. But without dissipative heating, we underestimate the intensification rate of the real storms. However, with the intensification, with the dissipative heating, and we improve this part. So this means dissipative heating is important, but it is important only for the strong storms. That makes sense. Dissipative heating is relatively small for the weaker stage of the tropical cyclones. Okay, so this is for one improvement, refinement. The second is we include the isosomer expansion. So isosomer expansion, that means the inflow. And previously in the previous theory, we just say that's there are pressure decrease, but there are some small contribution to the entropy surface flux because the pressure doesn't change much, assumed. But in reality, the pressure drops. Of course, the flux should be increased because of the decrease of the pressure. But this effect we found is important only for the strong storm stage, not the weaker stage. That makes sense. Weaker stage, the pressure decrease drop is not too large in the inner core region. Okay, so this is one of the results I should mention here. So this is the Kerry also saying his results using his model. Okay, so we run the model, the CM1 model, and we found the blue ones. That's the ensemble simulation, okay? So you can see the mean, ensemble mean. The red one is include the isosomer effect, but the blue one is without the isosomer effect. So that's support the idea isomer expansion can contribute to contribute to the maximum intensity and also intensification rate. But this contribution is marginal for the weak storm, but only for the strong storm you can get about 8 to 10% increase. Okay, so this is just a comparison for the intensification rate. Isomer expansion, there are some contribution to the control, but with the dissipative heating, that's a large contribution from dissipative heating. The dissipative heating is important, in particular for the high ST side. Okay, this is intensification rate. Intensification rate. You can see the time. That's a relative intensity. You can see the control, and this is, and you can see how important the dissipative heating. Okay, and isomer effect is some effect, moderate effect, you can say. Okay. So I think I should skip some of them. Okay, so but just one point here is ARC temperature difference is important. In previous studies, so the ARC flux is determined by the enthalpy differences. But enthalpy contains two terms. One is the temperature, one is determined by temperature differences, gradient. One is determined by the moisture difference or relative humidity in the boundary layer. But here we found if we separate the two components, we found the result is more sensitive to the ARC temperature differences. So here I show you this is the that's the MPI differences. Okay, so MPI can increase so much. Okay, control without the dissipative heating, without the ARC temperature differences. Okay, so include the dissipative heating, that's increases so much, but increases 1 degree ARC temperature difference. That's become this. This means the 1 degree ARC temperature difference can contribute to as much as the dissipative heating. This increase doesn't depend on the ST. The global warming, you may get the change of the AC temperature differences. I don't know, but if there are any increase, and then that's possible to increase the MPI and the intensification rate as well. Okay, so I spend another 10 to 15 minutes to finish the producing applications, because I think this over time that's fine. That's okay. Okay. So I think I just skip the summary because I already mentioned about the important points, okay, aspects of the theory. So application, the first application is quantifying the environmental effects on tropical cyclone intensity change. So you can see in the theory, there are no any environmental conditions, we said. No vertical wind shear, no dry air intrusion. So how we can consider the environmental effect in such a framework? This is I have some ideas, because previously there are no B here. That's just the efficiency term. That's the dynamic efficiency or ventilation effect. So we introduce the B here. B parameter. B is between 0 and 1. This just reflects all environmental processes that are detrimental to the moist neutral conditions of the IWTRC convention. I think this makes sense. Because we are simply the neutral condition. That means if we have a dry air condition, of course, neutrality will be destroyed or degraded. So we introduce the B here. That's the B is the function of vertical wind shear, the motion component of the storm. Why the motion is important? Motion can cause the asymmetrical structure, because the theory only considers the asymmetric vortex. And of course, there are also middle-level dry air intrusion, relative humidity in the middle troposphere. That's the environmental parameters, okay, not the internal structure of the storm. Okay, so the question is what to determine the B and how to determine the B. Theoretically, I couldn't do it. But empirically, based on the best track data, or if you have a bunch of the numerical simulations, we can use the model simulation to use the AI, okay, to train the theory, to get the B, how the B looks like. Okay? But this is not our purpose currently. We just try to use the machine learning to see what is determine the B here, okay? And what's the factor is most important to the intensity change. This is the paper we just accepted, okay, in JS just 2 days ago, okay. Just the day before yesterday, the paper accepted in JS. It's online abstract, but full paper is not published yet, okay. So currently we use the observational data, okay. We use the best track data and also the reanalysis data to determine the environmental parameter factors. So here, so we have the equation here, that B, because the best track data, we have the intensification rate, we have the MPI, we can have the relative intensity, because the intensity we know already, MPI we have, and we just inversely to get the B, okay? So we give these parameters. Of course, these parameters probably, there are some errors there, uncertainty, yes, there are uncertainty there. But compared with the uncertainty in the data, that's another uncertainty. So if you consider the uncertainty, you couldn't do anything, okay? But all the data, so many data put together, we still can get the useful information. That's our philosophy, okay, strategy. Okay, so the best track data, we can use the North Atlantic, Central Pacific, and also the Northwestern Pacific. So from the 1982 to 2021. Okay. So we have for the Northwestern Pacific, that's 1990 to 2020. So this is the distribution of the B, okay? The B parameter is here. And then the horizontal is the axis is the relative intensity. Okay, the color showing you the intensification rate. So what you see here, B is large and the intensification rate is large. If B is here, it's 0, the storm couldn't intensify. And B below this line, that's a weakening. A storm is a weakening. So this is just the intensification rate greater than 0, and that's the B must be greater than the square root of the relative intensity. This field told us. And what's the B? What's the distribution of the B? That's the probability distribution of the B frequency. So the red one is for all the intensification stage cases, and the blue one shows you the weakening or the insignificant change of intensity change. So you can see for this intensification storm, the B is pretty large. This is the 1, this is 0. You can see for the weakening storm, that's mainly this range, much smaller compared with the weakening storm. So B contributes to the intensification. That's by environmental conditions, okay? Environmental factors, including vertical shear and many other factors. We don't know yet. But we tried our best to see what's the most important factors. So this is just to give you the whole B, okay? We haven't looked at which B is important, okay? Which environmental factors. Okay, so we look at the different variables here. The current intensity of the storm, MPI, vertical wind shear, and also upper ocean heat content, and the divergence in the upper troposphere. The divergence in the upper troposphere, that's mainly focus on the weather synoptic scale conditions, okay? So if you have a subtropical high or the middle latitude trough effect, okay? So this determines the effect of the environmental divergence in the upper troposphere. And the middle level relative humidity, and also the DMPI. DMPI, that's the change of MPI along the track. That means the ST change. If the ST gradient is large, this maybe can cause some adjustment of the intensification rate to the changing ST, and also the motion speed of the storm. I mentioned the translation speed. So we tested these parameters, and I will not go to the details of how we can do it, because B supposedly is the function of different factors. The efficiency is not a plus, okay? So one factor and another factor, they should be multiplied. For efficiency, multiplied, not plus. Okay, so there's multiples of various factors, but we consider the 6 factors here. Okay, the 6 in total. Okay, and this is we couldn't do any machine learning. Machine learning couldn't do the nonlinear multiples, but we do the logarithm. Okay, we get the logarithm, and then we can get to use the machine learning to determine the functional relationship. And after we get the logarithm relationship, we can invert to this form. Invert to this, okay, to this. I will not give the details I mentioned, okay. So if you are interested, you can read the paper, okay. But I just give the ideas, what we did. And then I show you what we get. for the results. Okay, so this is the results for the period. I just shown you for different basins all together. We get for the intensity change contributed mostly by the vertical wind shear. Okay, and then the ocean heat content, upper ocean heat content, and divergence and middle level relative humidity, and the SAT gradient, and the translational speed. So the point is, this contribution by the environmental factor is different from previous studies. Previous studies, they took the best track data as the intensity change. But the intensity change may be contributed by the internal dynamics and also the environmental effect. But in use our theory, the internal dynamics component is already removed. This is totally, you can consider this totally environmental effect. This is the advantage using this approach to quantify the environmental effect. Okay, last is I can skip this because this is just a B. How the B looks like. Okay, B vertical shear ventilation. I just give you one example. Large vertical shear causes the B, reduce the B. Reduce the B, that means it increases the ventilation. Okay, that makes sense. Indeed. Okay. And for the intensification rate also here, that's a negative part. That's a smaller part. That means the large vertical wind shear is unfavorable for intensification of a storm. Okay. So I will not describe details here. Okay. But later on, I think the production, that's spend 3 minutes. Okay. So production, we just needed to predict the B here. We don't need to anything else. We know the B is the function of various environmental factors. So how we can determine the B? We use the machine learning here again. So I will not discuss the details, but we are drafting the paper. We just discussed it with Jing Shi yesterday at the reception. We discussed how to draft the paper. Okay, so I show you the flow charts. The flow chart is given time. At the given time, we have the intensity of the storm and we have the environmental factors. Okay, and we apply the same. We use some machine learning approach. Okay, we determine the B. Once we have the B, we just do the time integration. The time integration, we get the intensity at the T plus delta T. And once we have the new intensity, and then we can come back again, just a circle, time integration. Okay, so I show you how success, and also data set also important. Okay, we train the data with machine learning, and for the period of 1982 to 2021. Okay, the environmental factors are all from the GFS reanalysis data from the ships. Ships is the data set for the development of the tropical cyclone intensity prediction schemes. Okay, so we have a training period, and we left the 3 years for the testing verification. In total, that's the Atlantic, North Atlantic. In the 3 years, we have the 65 tropical storms. Okay, so we have the predictors. I will not discuss the details. The 6 climatological, 32 atmospheric dynamical, and 28 atmospheric thermodynamic factors. Of course, there are some overlapping here. So we are still trying to reduce the numbers here. Okay, I'll show you the results. So this is the training results. The training, that means just a hindcast. The training, that means we use the GFS analysis data, and then when we do the prediction, we also use the same data set as an environmental condition. I call it the testing. Okay, so this is the area bars. So this is the shallow ones. That's the maximum, the mean absolute area. And this is the root mean square area. Of course, root mean square area always larger than the absolute area. Okay? So you can see the mean absolute area that's used in many annual report. Okay, evaluation of the annual report. So what's the current stage for the area bars is about the 4 to 5 meters per second for 24 hours, and 8 to 10 meters per second area for 72 hours. That's large. However, train the model uses exactly the good input. That means the environmental factors get from provided by the reanalysis data. We can get the area is only below around 3 meters per second absolute area. That's amazing. Okay, so I show you the four predictions. So this is the red one is that's the hindcast. Okay, that's just a testing result. You can see how good it matches the oral peaks and transitions. Okay, so then we are excited. So good. We can do the prediction. Okay? And what's going on? This is a prediction. You can see the 65 storms. We change the data. The input is environment is not from the reinvest data, but from the GFS forecast. The forecast includes the track and also environmental factors. For here, you can see how large it is. The area now is much larger than the official forecast. Failed. You can say it failed. So what's going on? Then we try to check each of the input variables. We found is this guy caused the trouble here, C flux. See, what's the C flux? C flux is like the middle-level dry air intrusion, ventilation. C flux is the flux of the calculated from the surface, or difference between the surface and the average using the relative humidity below 5 hectopascal to the surface. So you can see the area is mainly produced by this guy. Okay, we retrain. We will drop this, we remove it. Okay, so this is the result. We retrain the model without the use of the C flux, and you see the results. It's not as good as what I showed you before, but it's reasonable. Becomes reasonable now. That means we have a room to improve this term. But we found in their database there are problems in this term, in this variable. So we are contacting with the JONAV to ask them to see what's happening and how to fix the problem there. Once we fix, we can improve our prediction. But here, that's the prediction without the C flux. You can see it's quite good. It's still, even to 5 days, we get the mean area is below 6 meters per second. That's very encouraging. Okay. So I think this is the oral results I want to say today. So from this exercise, we got to know the importance of the C flux. Makes sense because the middle level dry air intrusion is so important for the neutrality condition in the IOR region. Okay? So this is the compare. You can see how different. Okay? So the C, that's the contribution only by this parameter. Okay, this factor. Okay, so this is give you some case studies. Okay, so the red one is the trend and the blue one is the forecast. The tracker forecast for the four storm is not large, so you can get the pretty good predictions here. So I move very quickly for the future, and we try to put the maximum potential intensification rate for the operational use in HRD. That's what I plan to have my sabbatical there. And they are interested in give me a upper bound of the intensification rate. This may be good for the prediction of the rapid intensification, RI cases. Okay. The second is the long-term trends and global warming impact. This is part of one of my PhD students is doing this now because the SAT contribution to the MPI, and we have environmental factors, B. We can separate. We can do the historical data. We can do the projections, use the projection data. Okay. And then the theoretical predictability of tropical cyclone intensity. So far, using numerical model and whatever. So here, theoretically, we can get the area bars here. So you can see the tropical cyclone intensity prediction is very sensitive to the initial intensity area. In particular, in the weaker stage here, in the weaker stage, only small area in the intensity can cause large differences areas during the rapid intensification stage. So this is the area I'm looking at, getting into the details, later, in my studies. And finally, is using the framework to understanding the contributions by various factors to individual tropical cyclones. So here, I just show you some results here. So we just use the different factors. B is contributed by various factors for each storm. BI is each storm. And then we can see for each case, we can quantify which environmental factor causes the intensity change of the storm. Either rapid intensification or the weakening of the storm. I think I used too much time today, so I stop here and thank you for your attention. So this is the paper just published in the recent 2 years for this work effort.
Yeah, thank you so much. So your presentation was very smart, and it reminds me of what I was excited by your class in UH. Okay, so anyway, we have the 10 minutes remaining. So 10 minutes left. So please.
Thank you very much for the very interesting talk. I have a question about the simulation using the sounding from the Western North Pacific and from the North Atlantic. I read your paper about getting the real sounding from the Northwestern Pacific, and I found the Cape in the sounding has quite a significant value. It's on the order around 1,000 joules per kilogram. So I wonder, in your intensification theory, how does the Cape contribute to the intensification rate? Does it contribute positively or negatively to the intensification rate? And could you provide some rationale for that? Thank you.
Okay, that's a good question, and I haven't time to tell the details. Of course, yes, the sounding can affect the intensification rate, but not the theory can control that by the MPI. Okay, the maximum intensity will depend on the sounding and the ST. Okay.
Okay, thank you. I have a second question. In your formula, there's an H parameter, which I think physically it is the depth of fluid that is being accelerated or being decelerated. And you use the parameter of 2 kilometers.
Yeah.
And I wonder what is the reason to choose that value, not, for example, depth of boundary layer or depth of the whole fluid, which is 15 kilometers, and the former is the 1 kilometer. So how did you choose the 2 kilometer value?
Okay, the 2 kilometer, that's we consider for the tropical cyclone where mixed boundary layer. That's a very good option for the well developed cyclone. But for the weaker storm, we don't know. But we just use. But fortunately, we use the 2 kilometers, and then we get the quite consistent results from the full physics simulation and also observations.
Do you think
Perry may know better? I need to have a better answer on this because you use different values in your papers. I'm confused sometimes, But I'm still have some questions. We need to look at the details. But 2 kilometers so far gives the good results indeed. Yeah.
Okay. Thank you very much.
Just please, Lisa.
Thank you, Yuqing. Yes.
Hi.
Yes. Can you go back to the delta T 1 degree C slide?
Delta T1?
Delta T 1 degree C.
1 degree, okay.
Yes.
Oh, sorry. See. This one.
Yeah, I think maybe one.
This one.
Yes.
So what is the MPI here? MPI as a function of ST. This is the intensification rate just given 30 degrees Celsius ST. And this is the relative intensity.
So in 1 degree, delta T will change will compensate the...
This also motivated by the work we did with the Zheng Xu, my former PhD postdoc. So we found the variability of the MPI in different basins, different seasons, and the spatial differences. And we found the ARC temperature differences vary quite large. And on average, is 1 degree, but in the middle latitude is much higher than the 1 degree Celsius. So that's motivate us, say, ST and the relative humidity should be separated to see whether they can cause the differences. And then we found it's so sensitive to the ARC temperature differences here.
Okay. So, Sato-san.
Thank you very much for I'm not clearly understand the whole story, but I think your time dependency introduce the feedback processes. So I want to clarify traditional view or old view didn't have a feedback process. The Vmax, time-dependent Vmax is simply dependent VMPI. It's a source term. This doesn't have a feedback process. So I think your new theory introduced feedback processes. So, but this feedback is introduced as a large E initially and convert to B or A. So I think it's a key such a parameter to introduce feedback. So why? And the traditional theory didn't explain RI in this time-dependent theory.
Okay, that's a good comments and the question, and I should address, I think. And the first is I think from energetic point of view, you may agree we have a dynamical efficiency. This is learned from balance dynamics. So I consider my theory is just the combination, or there are two components. One is like the carrier theory, ARC interaction, positive feedback, which mechanism is here. Okay, because we have the MPI. MPI is just the steady state counter heat engine, but we extend it to the early stage of the storm. Okay, and then the E should be depend on the intensity of the storm. That's the balance dynamics tells us there are positive feedback there. So this is positive feedback included here. Use the E. Okay, is the intensity dependent. And the second is the A. That's the ventilation parameter. Ventilation doesn't mean the neutrality condition in the free troposphere, because the energetically based theory there are nothing in the free troposphere above the boundary layer, just the surface layer mostly. But only assume that the potential energy convert to the kinetic energy in the inner core column. Okay, nothing in the free troposphere. But in the dynamically based, we need to close the theory to the free troposphere is important. So we assume that the ventilation parameters.
Mm-hmm. Thank you very much. So yeah, I feel all the important dynamics processes are expressed as such a coefficient. A or
a coefficient?
E or A.
Or E or A.
Yeah.
They share the same dependence on the intensity.
I want to know some dynamical theory should explain such a
That's a good suggestion. I said I couldn't do it for now, but maybe we can. There are some smart young people who can do it. And I often asked by some young students. They say whether you can give the analytical, theoretically, how to determine the A or E. I say currently, I have no idea. But I think in the future, maybe some smart young researchers can fix the problem. And of course, there are some other factors, okay, like size, whether size matters to the RI theory. There are no any size parameters. But in numerical simulation, always we have the largest storm intensifies slowly, and the small storm intensifies more rapidly. There are no size dependence. But we have a paper now in JS. It's under review, maybe accepted soon. That's why we addressed why the theory don't have the size parameters. But we have the answer now, but I don't have time to tell here. We can discuss later.
Thank you. So almost time, but so Professor Carey, do you want to say anything? Okay, so is there last question or something? Comment? Okay, Yamada.
Thank you very much. Very nice, interesting talk. Because I'm from JMA, I'm very interested in the application of this theory for the operations, for the better prediction of intensity. You show the verification result. Have you conducted some verification against current ships? Because now JMA also used the ship's technique for the operational TC intensity forecast.
I think our next stage, at the initial development stage, was still okay. So we have the results here. I don't think it will change in our paper. The result is still the same. But for the operational implementation, we need more manpower and the support. But currently, I'm from the academic. I don't have a resource to do the operational implementation. But I will discuss with the HRD people and the National Heart Center in US, and also, of course, in China, we can try. But I hope in Japan we also can implement because several minutes, 1 minute, you can get the results. Because the training, the machine learning is always there. We have just the block the environmental parameter. You have the ship's data set in your operational setting, and then just use the parameter, subtract the variables from the database. We can do the prediction very quickly.
And also the equation you introduced, the theory of the intensity rate, is applicable to both. It doesn't choose a TC stage either before RI or after RI. And the forecasters at operations always are concerned about if this tropical cyclone is going to experience libido intensification or not. But if we analyze many cases for B, probably we can say something about if one particular tropical cyclone is going to experience RI or not. How do you have any thoughts and idea how this equation can be used for such kind of the onset, the timing of the RI?
I think that's a good question. So currently, you can see even our fitting here, test fitting, we still have error or there. If the perfect theory, there are no any error. The data is perfect and the theory is perfect. You shouldn't have any significant errors. But we still have significant errors. That means there are some uncertainties, including the CT and the CK. Okay? So we fixed the CA and the CT and the CK in our study because we can consider, say, there is the data, best track data. There is still uncertainty. Maybe the uncertainty is even larger than the CK and the CT. That's the reason we choose the constant one. We still get very acceptable results, not the perfect, but acceptable results. Yeah, very still promising. Yeah, good suggestion. And also, we also considered the other way, okay? So I haven't done yet. We use the data simulation and also machine learning. We can just not determine 1B. We also can determine the CT here. Okay? Because CT, we can be unknown. We can, in machine learning, we can have too many variables. We can get as an unknown in the system. We can get the like the inversely to get the CT as well. Thank you.
Okay, so when I finish, but so quick answer. I want to give you a quickly answer, yes or no. So, are your equation in the second part able to explain why the SST above the 26 degree to start intensification of tropical cyclone? That's climatological view, but needed to do the TC formation. Are you saying?
Well, that's a good question. And the current theory, there are no any cutoff at some sea temperature. Do you have any comments on that? No. So in theory, even the MPI, you give the ST sea temperature, you get a value, not necessarily say maybe no hurricane to develop there. Yeah, that's a good number.
So I'm afraid, so I need to finish this session. So very, very thank you so much. So please give the letter.